Section 3.4, Composition of Functions. Suppose we want to calculate how much it costs to heat a house on a particular day of the year. The cost to heat a house will depend on the average daily temperature, and in turn, the average daily temperature depends on the particular day of the year. Notice how we have just defined two relationships. The cost depends on the temperature, and the temperature depends on the day. Now, using descriptive variables, we can notate these two functions. The function c of t gives the cost c of heating a house for a given average daily temperature in T degrees Celsius. Now, the function t of d gives the average daily temperature on the day d of the year. Now, for any given day, the cost is going to equal the cost of the function t of d, which means that the cost depends on the temperature, which in turn depends on the day of the year. Thus, we can evaluate the cost function at the temperature t of d. So, for example, we could evaluate t of 5 to determine the average daily temperature on the 5th day of the year. Then we could evaluate the cost function at that temperature. So we could write it as the following. We would have c of t of 5. So the outside function represents the cost c for the temperature. The inside function is the temperature on day 5. So just like order of operations, you would work within and then out. So you would find out what is the temperature on day 5 and then find the cost for that temperature. Now, by combining these two relationships into one function, we have performed function composition, which is the focus of this section. Now, combining functions using algebraic operations. Function composition is only one way to combine existing functions. Another way is to carry out the usual algebraic operations on functions, such as addition, subtraction, multiplication, and division. We do this by performing the operations with the function outputs, defining the result as the output of our new function. Now, suppose we need to add two columns of numbers that represent a husband and wife's separate annual incomes over a period of years, with the result being their total household income. We want to do this for every year, so adding only that year's incomes and then collecting all the data in a new column. If W of Y is the wife's income and H of Y is the husband's income in year Y, and we want T to represent total income, then we can define a new function as the following. T of Y, which is the total, is equal to the husband's income in that year plus the wife's income in that particular year. Now, if this holds true for every year, then we can focus on the relation between the functions without reference to a year and write T equals H plus W. Just as for this sum of two functions, we can define difference, product, and ratio functions for any pair of functions that have the same kinds of inputs, not necessarily numbers, and also the same kinds of outputs, which do have to be numbers, so that the usual operations of algebra can apply to them, and which also must have the same units or no units when we add and subtract. In this way, we can think of adding, subtracting, multiplying, and dividing functions. For two functions, f of x and g of x, with real number outputs, we define new functions f plus g, f minus g, f times g, and f divided by g by the relations. So whenever you're given this form, parentheses f plus g of x, you write the definition out as taking the function f of x plus g of x. If you have f minus g of x, it's going to be f of x minus g of x. F times g of x is the same thing as taking the function f of x and multiplying it by g of x. F divided by g of x is equal to the function f of x divided by g of x, where g of x cannot equal 0. So again, I want to stress the importance that whenever you see this scenario, you want to make sure you write out the definition.